Today's topic is operational amplifier. In this lecture, we will discuss the basics of operational amplifier. So, as the name suggests, operational amplifier is an amplifier. This amplifier is having a very high gain. So, if it is an amplifier, it will amplify the signal as the normal amplifier do. So, here we can see at the input side, this input signal is having a less amplitude, but as we pass it through the amplification circuit, it will amplify the input signal and give the high value of output signal. So let us understand that why it is known as operational amplifier. So when digital computers were not evolved at that time, mathematical operations like addition, subtraction, integration and differentiation were performed by using this operational amplifier. So by connecting some resistors and capacitors together, differential operations can be performed. That's why it is known as operational amplifier. Operational amplifier in short is also known as op-amp. This is a symbol for operational amplifier. It is having a two input terminals. One is non-inverting terminal and another one is inverting terminal. And it is having two supplies. One is positive supply, another one is your negative supply. This could be plus VCC and minus VCC, or plus V saturation and minus V saturation, and it is having a one output. So from here we have concluded that this operational amplifier is having a two input terminals, one output terminal and two power supplies. And the input terminal, which is marked by this positive sign, is known as non-inverting terminal, and where the input terminal, which is marked by negative sign, is known as inverting terminal. So one input is positive and another input is your negative. So output obtained here will be the difference of this input voltage. That's why this amplifier is one kind of differential amplifier, because it amplifies the difference of input signal. For example, if this input voltage is V1 and this inverting terminal voltage will be equals to V2, so at that time output voltage we will obtain is equals to the amplification gain of the amplifier A multiplied by V1 minus V2, where this A is the amplifier gain and this is open loop gain, which means that output is not feedback to the input side. So this is amplifier gain, and in operational amplifier this gain is very high. Its value is from 10 raised to power 5 to 10 raised to power 6, which is very high value. And the output voltage is equals to amplifier gain A multiplied by V1 minus V2, where V1 is the non-inverting terminal and V2 is inverting terminal. This is the pin configuration for the op-amp and its IC number is 741. It is having a 8 pins, 1 2 3 4 5 6 7 and 8. This is 8 pin type IC, where at the second pin inverting terminal is connected and at the third pin there is a non-inverting input is connected and output is obtained at the sixth pin, where the plus VCC will be provided at 7th pin and the minus VCC will be provided at 4th pin, and 5th pin and 1st pin for the offset value. And this is the 8th pin is not connected, means this pin is not in any use. So this is the how a IC of op-amp look like. IC 741 looks like. So as we discussed in last slide, that output obtained if there is two inputs, one is V1 and another is V2. So output voltage what we will obtain is the difference of input voltages. So for example, if inverting terminal input is grounded, which means that V2 is equal to 0. So output obtained here will be equals to A times of V1 minus V2, where V2 is equal to 0. So output will comes out to be A into V1, which means that output is purely non-inverting output, which means that if we provide a sinusoidal signal here, at the output side we will have amplified signal, or which is in same phase to the input signal. For example, output we concluded that output is equals to A into V1. If A value is V1 value is equals to 1 volt and A is equal to 10, then output V out will be equals to 10 into 1, which is equals to 10 volt. So from here you can see that at the input we have provided only 1 volt, but at the output we are getting 10 voltage, which is uh, this is we obtained because input voltage get multiply to the open loop gain, so which increase the uh, input value at the output side. So in next, if we ground the non-inverting terminal, which means that V1 will be equals to 0. So at output we will get a V1, which is 0 minus V2. So ultimately output will comes out to be minus a V2. So this minus sign will shows that output is 180 degree out of phase, which means that if output is this one, so at the output side, if input is like this sinusoidal, so at the output side we will get the inverted output, which is a 180 degree out of phase. So output will be in this way, where this magnitude will be high. Magnitude will be equals to A times of V2, and here the magnitude is only V1. We can also consider it like, if V1 is equal to 0 and if V2's value is equals to 1 volt, at that time output voltage obtained here will be equals to A into V2, and if A's gain is 10, this will be minus 10 volt will be obtained at the output side. So this we are getting a negative value at the output side. So that's why it is known as inverting input, because output obtained here is negative value. That's why it is inverting value, which is where output it provides the 180 degree out of phase. And if there is a V1 and V2 both are present, so at that time Vd will be the difference of this voltage V1 minus V2. So output obtained here will be equals to A into Vd. So let us understand the voltage transfer characteristics of the operational amplifier. This is the plot between difference voltage, which is V1 minus V2, difference of input voltages, and output voltages. At the x-axis there is Vd, and at the y-axis there is V0, and this slope represents the amplifier open loop gain, whose value is lie from 10 raised to power 5 to 10 raised to power 6. So for example, if this value A's value is 10 raised to power 6, so at that time this, and suppose if this Vd is equals to 1 microvolt here, So output, V output will be is equals to A into Vd, which means 10 raised to power 6 into 1 into 10 raised to power minus 6, which is microvolt. So here output will comes out to be 1 volt. So for this 1 microvolt, V naught output will be equals to 1 volt. And similarly, if it is a 2 microvolt, so V naught will comes to be 2 volt. And if it is a 10 microvolt, the output V naught will comes out to be 10 volt. So one time will come that, and then which is if we are changing the, if there is an increase in the difference of input voltage, there will no change at the output side. So that value will be fixed to the plus V saturation or to the plus VCC at the positive side, and to and in minus VCC and to the minus V saturation at the negative side. So this is the voltage transfer, this transfer characteristics of the amplifier, operational amplifier. And this is the basic equivalent circuit of operational amplifier, where this Zin shows the input resistance or input impedance, and this is the Z out is equals to output impedance of the amplifier, and where this is V in, V1 is here inverting terminal, and V2 is here is non-inverting terminal, and V out is the output we are obtaining here, and here we are obtaining a gain A, and V difference is the difference of input voltages. At the output side, output will be obtained as equals to A into V2 minus V1. V2 is your non-inverting input and V1 is your inverting input. If we are talking about the ideal characteristics of the operational amplifier, before going to the practical amplifier, we will discuss the ideal characteristics of operational amplifier. So in this case, this input impedance should be infinite, which means that whatever inputs are provided to the operational amplifier will be directly fed to the to the operational amplifier. That's why it should be infinite, where this Z out or the output impedance should be equal to 0 ideally, so that whatever output is operational amplifier will have, that will not have any drop at the this this output impedance. So this output impedance is kept 0 and the input impedance is kept infinite. So whatever input is coming is goes to this amplifier circuit, and whatever this amplifier circuit will gives the output to this load, so that will directly provide it to this load without any drop in another resistance or impedance. And the amplifier gain, so from here we have concluded that input resistance or impedance of the operational amplifier is infinite, output impedance is 0, and the amplifier gain, as we already said, is very high, from 10 raised to power 5 to 10 raised to power 6. So ideally it will be equals to infinite. This is and the bandwidth will also be equals to infinite for the ideal amplifier, which means that it should the frequency, this operational amplifier will be for the frequency range from 0 to infinite. That's why bandwidth is infinite. And there are another factors like slew rate and CMRR. So we will understand this one by one. What is slew rate and what is this CMR, common mode rejection ratio. So first of all, slew rate This slew rate is basically how fast operational amplifier is able to reach its final value. So let us understand at the input side if the difference of voltage is equal to this, and at the output side we are obtaining a signal like this. This is V, this is 0, and this is your V set. Its highest value is your plus V saturation. So at the output side, this value is varying from 0 to V saturation. So in ideal op amp, it should reach to the 0 to V saturation at in 0 time. In 0 time means there should be a no time will be taken to reach this value from 0 to V saturation. So this is known as the slew rate. For slew rate, this time should be 0, which means that operational amplifier is having a fast slew rate, high slew rate. So for ideal operational amplifier, this slew rate should be infinite. So another is your CMRR, common mode rejection ratio. So common mode rejection ratio is equal to difference of VD by VC. Sorry, not VD, this is AD by AC. This AD is the for the differential gain, and this is common mode gain. So this can be understood if this V1 and V2 are same. If V1 is equals to V and V2 is also equals to V, at that time output voltage will be equals to A V2 minus V1, where these two values are same. So V out will be equal to 0. This output voltage is equal to Z0. So there will be no output voltage, which means that if input voltages are same, so at that time we are not having any output in the operational amplifier. But if there is different voltage, if V1 is not equals to V2, at that time we are having some output voltage, and only then this amplifier will amplify the signal. So CMMR is how well an amplifier is able to reject the common input voltages that is being applied to both inputs terminal, and how well it amplify the difference of voltage applied to its input side. So common mode rejection ratio should be equals to infinite for ideal op amp, where I have already told you its value is equals to AD upon AC, where AD is the differential gain and AC is equal to common mode gain. So let us see the ideal op amp characteristics, where the input impedance we have already discussed, it should be infinite, and output impedance should be equal to 0, and open loop gain, which is A, should be infinite, and offset voltage should be equal to 0. This offset voltage is equal to 0 means when there is no input, there should be no output. So if we are providing some input, if there is a no input is provided at the input terminals, but still there is some output voltage, then that voltage is known as offset voltage. But for the ideal op amp, this offset voltage will be equal to 0, because for no input there should be no output, and this slew rate should be infinite, and CMRR, common mode rejection ratio, should be infinite. So let us discuss about the practical specifications of op amp, which is op amp 741. Input impedance is high, which is around 2 mega ohm. Output impedance is 75 ohm, and where the open loop gain, which is A, is around 10 raised to power 6, 10 raised to power 5 to 10 raised to power 6, and offset voltage is 1 millivolt, which means that when there is no input provided to the operational amplifier, but at the output side there is still some voltage, which is known as offset voltage. So this is around 1 millivolt in case of practical operational amplifier or practical op amp. Slew rate is equals to 0.5 microvolt per microseconds. This is the unit for this slew rate is volt per microsecond, and common mode rejection ratio is 70.9 dB. So this is all about the basics of operational amplifier. Rest the rest of the topic regarding this operational amplifier we will discuss, or we will cover in another videos. So thank you.